All right, thanks for coming. So today we're pleased to have Maria Chudnovsky from Princeton talk about anti-complete subgraphs, right?
All right, well, thank you for having me. Thank you for coming. It's a pleasure to be here at IBS as always. So anyway, this talk is about a very recent theorem that we proved with Sepher and Sophie, but first I'll give you some background about the project in general, and then we'll get to the more recent results. So it's about graphs. Graphs have vertices and edges, and I'm mostly interested in families defined by forbidden induced subgraphs. So you fix a graph, or maybe a family of graphs, and you're interested in all big graphs from which you cannot get these little graphs by deleting those. And okay. Sanjay, should I skip this slide?
Maybe.
Let's skip this slide. Everybody. Does anybody not know what an induced subgraph is? So you know what induced subgraphs is. And the family is hereditary if it's closed under taking induced subgraphs. I drew this picture for the first time when I was a grad student, so 20-something years ago, and then I keep transferring it from one set of slides to another. So historical, and most pictures online of me giving talks is me on, with this slide in the background. I was taking a picture right in the beginning, so this is really. So one of the most well-known hereditary families, one of the most well-known families closed under induced subgraphs is a family of perfect graphs, and just to remind you what they are. So it's something to do with color, right? So if you want to color a graph, there's an obvious lower bound on how many colors you need to use, and that's a click number. And there are some graphs where this bound can be achieved. There are some graphs where the click number is 2 and chromatic number is arbitrarily large. But there are some graphs where it's not like that, where you can color with as many colors as the size of the largest click. And these graphs are interesting and nice, and it turns out you can make them even more interesting and nice by closing under induced subgraphs. So if you say the chromatic number and the click number are the same for all induced subgraphs, then that becomes an even nicer property, and these graphs are called perfect. Just for notation, chi is the chromatic number and omega is the click. And so there are several nice things about perfect graphs. For example, there's a forbidden induced subgraph characterization. Right? You can describe explicitly all graphs that are not perfect and minimal not perfect. So what are they? They're odd cycles of length at least 5 and complements of odd cycles of length at least 5. If the only reason for a graph not to be perfect is if you contain one of these or one of those. So that's called the strong perfect graph theorem. It was conjectured by Claude Berge, and then we proved it with Neil Robertson, Paul Simon, and Robin Thomas in 2003. But when Berge first defined perfect graphs, he made another conjecture about them. The conjecture that they're closed under taking complements. So a graph is perfect if and only if its complement is perfect. Now, if you know and believe this conjecture, if you know this theorem, then of course perfection is invariant under taking complements, because you see that the obstructions are a set of obstructions invariant under taking complements. But if you didn't know that, if you just met Berge and he told you his weak perfect graph conjecture, that's kind of amazing. How one would jump from this definition, the defining property of perfect graphs, which is something to do with coloring, to the property that taking complements doesn't change. So, but we could see the future. So in fact, it is true. It's a theorem of laws. And then so there are more surprises about perfect graphs. There's some people who understand polytopes can tell you many interesting things about them, but I'm not going to do that. But instead, I'll tell you that perfect graphs behave surprisingly nicely, algorithmically. So what does that mean? There are problems that are anticomplete in general, but you can solve them in polynomial time if you promise that the input is perfect. What kind of problems? Well, for example, computing the size of the largest click, or slightly more generally, put weights on vertices and look for the weight of the heaviest click. And then another problem like that is computing maximum stable set or maximum weight stable set. So because perfect graphs are invariant and taking complements, computing the click and computing the stable set is the same problem. but still surprising. Another problem is coloring. So because you can compute omega and it's a perfect graph, you have already computed the chromatic number, but what if you actually want an optimal coloring? Again, you can do that in polynomial time if the input is perfect, and all these problems are NP-complete for general graphs. Now, so let's go back to omega, but it's all the same. So the way you do it, it's a theorem of Groce, Lowas, and Schreiber. They record the problem of computing omega as a semi-definite program, and then they use tools from combinatorial optimization to solve this semi-definite program. Because the graph is perfect, it actually gives you the integer size of the clique and not something fractional. And the problem I always like to mention is, do this without the ellipsoid method. Do this, but find an algorithm to compute omega and perfect graphs, but an algorithm that you can describe in terms of the graph without doing something else first. I mean, one problem with this question that I like to ask is that I don't know how to ask it precisely. Right? What does it mean in terms of the graph? The semi-definite program is in terms of the graph. but I mean, somehow we're all humans, so you understand what I mean. Sophie Spirkl suggested that a combinatorial algorithm is one that doesn't use division in the description of the algorithm. So that will do. But I mean, I don't know, find a graph theoretic algorithm to compute. And you think, the way this proof works, you prove a lot of theorems about the structure of perfect graphs. You prove that they're all like this or like that, or break apart in certain ways. So then you think you take all this structural knowledge and you can turn it into an algorithm. Except it doesn't work. It doesn't even turn into a recognition algorithm. So, nice open problem. Do this combinatorial. Okay. So this slide was advertisement for hereditary families. So now that you've seen how wonderful they are, you could ask, are all hereditary families nice? Do they all have nice properties? And the answer is not at all. So for perfect graphs, the clique number and the chromatic number are the same. But in fact, it's not even true that you can always bound the clique number as a function of the chromatic number. So for example, in triangle-free graphs, you have triangle-free graphs with arbitrarily large chromatic numbers. So the clique number is 2 because it's triangle-free, and the chromatic number is as big as you want, so there's no function that would do that. And that's a perfectly fine hereditary family, it would be the triangle. So algorithmically also, in general, it's a mess. You can't it's NP-complete to compute omega, even for graphs with no stable sort of size 3. What we got for perfect graphs was not something that works in general for all hereditary families. So one might start thinking that forbidding induced subgraphs is not such an interesting property, just somehow locked out with perfect graphs. But then comes the early-final conjecture that tells you that actually there is something interesting about forbidding induced subgraph. And what do I mean when I say interesting? Well, when you just tell me that my graph doesn't contain this 10 vertex graph as an induced subgraph, that's a property of 10 tuples of vertices. That's a very local property. And what what one might ask is, does it tell me something global about the graph, or is it just some fiddly property on the 10 tuples of vertices? And what the Hajebi conjectures is that there is something global. If I tell you something about all 10 tuples of vertices, so that they don't make a certain induced subgraph, then something happens to the graph globally. So what kind of something? Well, you suddenly get either a clique or a stable set, which is much larger than you would in a random graph where nothing is forbidden. So what does it mean? Well, the conjecture is that for every h, there's an epsilon, so that if you don't contain h as an induced subgraph, then either the clique number or the stability number is at least the number of vertices to the power epsilon, where epsilon depends on h. And in the random graph, it's log n. Now, I should mention that this is a conjecture. If you didn't ask for this to be number of vertices to some power, but just asked for some function that's better than log, that's log. Already Erdős and Heinel proved that you can get, so you forbid h, and you get a clique or a stable set. Of this size, and there have been improvements to this function recently. So somehow to prove that it's not like in a random graph, that's been known for a long time. But to get all the way to polynomials still. Alright, so that's the channel conjecture, which I'm not going to talk about anymore, but it just seems to me if I'm going to give any talk about induced subgraphs, I should mention the channel conjecture. Okay, so moving on. Well, so perfect graphs are very nice, and some hereditary families are not nice at all, so that opens the door for an infinite question, which family is nice? And what I want to talk about now is two related versions of being nice. Which families have interesting structure, and for which families can I design efficient algorithms? The question that I'm not going to think about is this question: when can I bound the chromatic number as a function of the click? That's another interesting question, but I'm not going to touch it. We're just going to do structural algorithms. And when you think about structural algorithms, there's a tool that was developed, works for that perfectly, and that's the tool of tree-decompositions. So people who know what a tree-decomposition is, can you raise your hand, please? Okay, so so I'm going to spend some time on this. This is this is kind of this is for a very niche audience, because if you know what the tree-decomposition is, you really don't need this slide, and if you don't know, then you're not going to learn by looking at one slide. The people who know what it is are laughing. But this is for people who kind of know but forgot. And then if you don't know, then it's okay. I'll say enough other things that the gist of the talk will be clear. So what's a tree-decomposition? Well, it's an attempt to represent a graph by a tree. Right? Trees are very nice. You can run any algorithm you want on trees. We understand the structure very clearly. So now I give you a general graph, and I want to say, well, this graph, in some sense, it's not too far from being a tree. Or I'll give you another general graph and say, well, this graph is very far from being a tree. So here's how you do it. So you have a graph G, and the tree-decomposition is a pair T and chi, where T is a tree. And then what you do is to every vertex of the tree, you assign a set of vertices of your graph. And you call it the bag at that vertex. Right? So for every vertex of the tree, there's a bag at V, which is just a subset of the vertices of the graph, and there are some rules. So somehow you're trying to represent your graph, so you need to capture something. You need that every vertex of the graph you're trying to represent appears in some bag. Well, that's fair. You have to keep track of all the vertices. You need that every edge of the graph you're trying to represent appears in some bag. And then the last rule is that somehow there has to be some order to it. You can't just throw vertices and edges wherever you want just to make sure you've listed all the vertices and all the edges. And the rule is, if I look at the vertex of the graph I'm trying to represent, and I see where it appears on the tree, that has to be a subtree. That has to be a connected graph. Right? The support of x, so in other words, the vector where it appears, make a subtree of t. So that's it. So if I have that, then I consider that I represented G by T using the map chi. So let's do some examples. So this is G, and I'm going to use the same tree to represent it. So all I need to tell you is what to put in bags. And here's how I'm going to do it. So I fix a root for the tree, and then for every vertex in the tree there is a unique path to the root because it's a tree. And then I look at the vertex, I look at its unique path to the root. It has a unique neighbor in this unique path to the root. And that's what I'm going to put in the bag for that vertex. So for example, here I fix the root 3. Here's vertex 1, its unique path to 3 is 1, 2, 3. Its unique neighbor in this path is 2. So on this vertex, in the bag on this vertex, I'm going to put 1 and 2. Here's 4, its unique path to the root is 4, 3. Its unique neighbor in this path is 3. So I'm going to put 3, 4. So far it doesn't seem like a great accomplishment, because I had a tree, and its vertices had numbers, and now I have the same tree, and now every vertex is associated with 2 numbers. So it seems like I make things more complicated instead of simple. But it's going to pay off. So now let's do this graph. So this is not a tree. So then what you do is cover one. Now it is a tree. So you take, you can build a tree decomposition of this, maybe using the algorithm I just told you, or maybe doing something else. And this is where I'm building the tree decompositions. This is the tree. And now if you look at these bags but ignore one, you'll notice that it's a tree decomposition of the graph, of this graph is one covered. So now what do I need to do? I need to add one to some bag. And there's also a rule that I have to, there needs to be some bag that contains 1 and 2, because it's in H. So there needs to be some bag that contains 1 and 6, because it's in H. So I should add one here, and I should add one there. And then there's a rule that 1 needs to appear on the connected graph, so I have to add 1 here and there. And that's how you get this tree decomposition. Okay, so a couple of things. So here something improved, right? Because this graph had a cycle, and this graph is a tree. Now the bags are still pretty big compared to the size of this graph, but I could have started with a cycle on 1,000,000 vertices, and still the same procedure would give me bags of size 3. So we did something. So now, remember the goal of this was to say some graphs are like trees and some graphs are not like trees. So I need some measure to distinguish simple tree decompositions from complicated tree decompositions. And the way you do is you just define the width of the tree decompositions, which is how big the bags get, how many vertices of the graph get associated to one vertex of the tree. Right, because here's one tree decomposition you can always do. Take a one vertex tree and put all of V of G onto this vertex. So that's the tree decomposition, but you didn't gain it. It's very complicated. So, okay, so the width is how big a bag gets, and then the tree width of a graph is the minimum width of all its tree decompositions. And we say G has small tree width means it's close to being a tree. And then the tree width of a tree is 1, right? As you saw here, we started with a tree, and we did this example of a tree. We could do it to any tree. We constructed a tree decomposition with all bags of size 2, which means its width is 1. And then it's a theorem that if you're not a forest, then your tree width is not going to be 1. So the fact that here we need a bag of size 3 was a lack of trying, but it's really, you have to. Okay, so that's tree decompositions of tree widths. And the reason people like tree decompositions so much, well, first of all, it somehow capture a lot of the graph just by thinking about a tree. But also more concretely, you can use tree decompositions to run algorithms, design algorithms. If you're given a tree decomposition of small width, you can solve all kinds of problems efficiently. More efficient, by efficiently I mean it's going to be polynomial where the degree of the polynomial number of vertices of the graph, where the degree depends on the width of the decomposition, but not on the graph you separate. So what problems can you solve? Well, for example, you can find the stability number, right? Biggest stable set, optimal coloring, all kinds of things. So feedback vertex set, all the weighted versions of these problems. And in order to do that, you use a technique called dynamic programming, which I'm not going to describe, but I just want to say one thing about it. So what that technique does, you look at one bag at a time, and you look at all possible optimal solutions. Or you look at how an optimal solution to your problem in the whole graph might intersect this bag. And then you want to think about this possible intersections. And when so the key to success when you do dynamic programming is that you can efficiently look at all possible ways in which an optimal solution can meet the bag. So let's say we're thinking about max weight stable sets, so then you want to look at all possible maximal stable sets in the bag. Well, when the tree width is bounded, you can definitely do that because the size of the bag is a constant. So at constant time, you can look at all subsets of the bag, not even all maximal stable sets, but all subsets of the bag. But that's too much, right? I don't need to look at all subsets of the bag. I just need to look at all the ways in which an optimal solution can intersect the bag. So for maximum stable set, I just need to look at all maximal stable subsets of the band. And I don't need to do it in constant time, it's enough to do it in polynomial time. So somehow there's a big gap between what bounded treewidth does and what you actually want. And people noticed that a few years ago and started thinking about a different width measure called tree independence number, which is designed exactly for that. It's designed so that you can look at all maximal independent sets in the bag in polynomial time. And that's called tree independence number of the graph. And I'm not going to talk about it, but I wanted to advertise it. So, but we're going to go back to just treewidth. So small treewidth is very good for you. You can run algorithms. The graphs are easy to understand. So we want to know which hereditary families have small treewidth. Which hereditary families can you get a bound on the treewidth of all graphs in this family? And this is not the first time somebody asked a question like that. In the 1990s, Paul Seymour and Neil Robertson worked on a similar problem for different containment questions. What minor free families have bounded treewidths, what subgraph free families have bounded treewidths. So this is somehow a natural next step because now induced subgraphs are in fashion. But that's kind of the general problem of thinking about what hereditary families have bounded treewidths. And in order to answer this question, a good first step is to construct some examples of graphs with large treewidths, right? Never going to be able to prove it. So what graphs have large treewidths? Well, the complete graph has large treewidths, so large compared to its size. The complete graph has treewidths in size -1. The complete backtie graph, KNN, has treewidths n. And so far that makes sense because having small treewidths means being similar to a tree. These two graphs are very dense, so somehow our intuition is if you're very dense, you're nothing like a tree. So far so good. But now here's another graph, which is not dense at all. I'll describe it to you in a second. And it has very large treewidths. So what is this graph? So what's drawn here is called a wall. And I won't define it exactly, but you see what it is. And then you can subdivide some edges, and that's a subdivided one. And already this graph itself is not very dense, right? It's a cubic planar graph. And if you subdivide edges, that's even less dense. And yet it has huge treewidth. Its treewidth is as big as its height or its width. So that's at first glance is counterintuitive, right? If you're sparse graph and has large treewidth. But the thing is, the correct intuition behind treewidth is not density, but small cut sets that break the graph in a balanced way. Right? In a tree, you can delete a vertex and the tree breaks more or less half and half. And that turns out to be kind of the correct way to think about bounded treewidths. You can delete a small set of vertices and break the graph more or less half and half. So you can't do it here or there, but you cannot do it here either. If you play with it, if you delete any small set of vertices, the vast majority of the graph remains on one side. Okay, so that's another example. And for subgraphs, that's it. So it's a theorem of Robertson and Seymour that if you have large treewidths, then you contain a subdivision of this as a subgraph. For every t there is c, so that if the treewidth is bigger than c, then you contain a subdivision of t high, size t of this as a subgraph. But for induced subgraphs, there's a lot more going on. For example, one thing you can do is take the line graph of this. Right? So take a subdivided wall, take its line graph, it looks like this. So these junctions become triangles and then some subdivided edges. And in here it's the same story. You don't have small balanced cut sets. Well, this also has large treewidths. And yet this is not an induced subgraph of any of those because this doesn't have triangles and this does. And this is not an induced subgraph of any of those because this has clause and this doesn't. So this is another new family of obstructions to bounded treewidth. Okay, so that's something that people thought about at some point. And then there was a question, maybe that's it. Maybe it so happens that you just take line graphs and you've listed all the obstructions, but turns out the answer is not at all. So Cintiari and Tornion constructed a family of even pole-free graphs, so that means no induced event cycle. So no induced event cycle, no K4. and this family contains graphs of arbitrarily large trees. So let's just see what the connection to this picture is. So C4 is K22, right? So because there are no even holes, you forbid this. K4, there's no big clicks because K4 is forbidden. Now, this contains a tail, two vertices with three, I think it looks like this. Two vertices and three induced paths between them, anticomplete to each other. So you know two of these three paths have the same parity, say this and that, but then this is an even hole. So if you don't have even holes, you don't have that. This contains what's called a prism, two triangles and three paths between them. Again, two paths have the same parity. You look at that, it's an even hole. So this contains an even hole. So the family they constructed really doesn't have any of those guys, and yet contains graphs of arbitrarily large trees. So that's what it says here, and that means there are other obstructions. It's not enough to just list walls and their languages. Okay, so that was sad news. So now the question becomes, if I forbid KT and KTT and a subdivided T wall and the logarithm of a subdivided T wall, what else do I need to exclude? So let me call these obstructions T basic, and then let's say, just to say some words, a graph is T clean if it doesn't contain a T basic obstruction. And then the question is, what do you need to exclude from a T clean graph to guarantee bounded treatments? Now, somebody once asked me why these obstructions are called basic and others are not. That's just an historical remark. These were known and the others came along. So they're not basic in any deep way, they're just basic in the sense that they're the base of our knowledge. Okay. So people started thinking, what do you need to exclude? And then Laws and then Rascon proved a very nice theorem. So they were able to describe exactly all finite families, excluding which guarantees bounded treatments. Now notice this is somehow a little bit in a different direction than saying T clean and what else. Because as soon as I forbid subdivisions of something, that's an infinite family, right? So this question is forbid, KT and KTT and this infinite family and this infinite family and something else. And they asked a different question. They said, what finite families forbid? So and their theorem is that if you have a finite family forbidding which, so if F is a finite family forbidding which guarantees bounded treatments, that's if and only if some graph in F is a clique, some graph in F is a complete vector graph, some graph in F looks like this. So it's a graph, each of whose components is a subdivided K13, and some graph in F looks like that. It's a graph, excuse me, each of whose components is a line graph, right? So there are four graphs you have to have. And so the only if part is not very hard. The if part is right. So then forbidding one of this, one of this, one of this, and one of those guarantees bounded treatments. That's a very interesting proof. And I'm going to tell you something about this proof. So I'm going to tell you not how they did it, but how they would have done it. They would have done it in 2024 because it's their idea. But then a lot of kind of information we know now is thrown into it. Okay, so a KL brick is you take a complete graph on K vertices and you replace every edge. You replace every edge by L parallel edges. And I realize it's a bad name because brick already means something else. I haven't thought of a better name yet. So it's not the bricks you know, it's something completely ad hoc for this talk. And if somebody has a better name, which is describes this graph nicely. Complete graph and you replace every edge by L parallel edges. Oh, and then you take a subdivision. So for example, this is a 3-2 brick. I started with a triangle, I replaced every edge by 2 parallel edges and then I subdivided. So it's a theorem that reassembled with Darabi, Shali, Baldwin, Echo, Sepher, Hajebi, and Sophie, Spirkl, but it really follows from kind of a lot of things other people prove. So if you're T-clean and you have large tree widths, then you contain a KL brick. Right? Fix your favorite K and L, and then there's some tree widths that depends on T and K and L. So that if your tree width is bigger than that, then you contain KL brick.
So T-clean was no T-basic.
Yeah, that's right. And let me not tell you the proof, but somehow you take all of these results that people proved and then you put them in the right place. So, okay, so you contain that. Now here, contain it as a subgraph, not as an induced subgraph. Right? If you contain a KL brick as an induced subgraph, then you contain anything you want as an, or you contain a subdivision of anything you want as an induced subgraph. So what we need to do now is go from this KL brick subgraph to something in terms of induced subgraphs. And the way you do that is by using Ramsey theory. You look at scale brick and you look at small pieces of it and you start hitting it with various theorems of Ramsey as hard as you can, and you get this and that. And that's how Rosen and Artkon's proof would go if they proved it now. And then they did something similar, just the terminology was a little different. But actually you can hit much harder, and then you get a theorem that we proved, again with this set of numbers. So now we want to ask the question, if you remember, we wanted to know what you need to exclude from T-clean graphs to get bounded tree widths. So the first question in this line of thinking would be, what if I just exclude one more graph? You're T-clean and you exclude one more graph. What graphs work? And so the proof I just described to you, where you produce a KL brick and then start saying what it must contain as an induced subgraph using Ramsey, tells you excuse me, it must contain something like this. It must contain a graph, all of whose components is a subdivided star. Right, so for Rosen and Artgon it was K subdivided K1C. For us it's a subdivided general star. But remember, we already forbade subdivided walls and the like. So what I just described to you proves that if your graph is T-clean and doesn't contain some graph that looks like this, then its tree width is bounded. Now, how about only? Right, so only if is not clear yet. But for only if you need more examples of obstructions. Here they are, so there are two. One is due to Bohot and Davis, and one is due to Bonamiento. And there's some others known now, but these I'll need later in my talk. So let's see what they are. So this is, you take a bunch of pairwise anticomplete paths and a stable set of vertices. And what I've drawn here, every vertex has one neighbor in every path, and the neighbors are all in order. But you can make it a little bit more tricky. You can here are the paths, and here are the vertices, and give each vertex some neighbors on the path, not necessarily one. But do it in such a way that they don't interfere with each other. So each vertex on each path has an interval where it's allowed to have neighbors. And it only has neighbors only there, and it's all in order. Right? So that's one example. And when I say Bohot Davis, I'll always mean that kind of picture. And then this is another example that's called the Death Star. So let me first explain to you what's drawn here, and then I'll tell you how to generalize it a bit. So you start with the path. Actually, we have to start with the path. You take a vertex, give it a neighbor. So this partitions the path into two intervals. You take another vertex, give it a neighbor in each interval. That partition, so now you have 4 intervals. Now take another vertex, give it a neighbor in each interval. Now you have 8 intervals. Now take another vertex, give it 8 neighbors. So that's called, in general, a T-Death star. So that's a t-dester, right? Added t-vertices. So now I want to allow some more neighbors. So the rule is, it's how it is, right? One person starts copying and everybody starts copying. So the rule is, so he made this interval and that interval, but the intervals among its neighbors I don't copy, I don't have to break them. Now he needs to have neighbors here, neighbors there. So now I have sort of 4 important intervals, right? So like an interval is important if it goes from a neighbor of one guy to a neighbor of another guy. And what I need to break is this important intervals. I'm sorry, I just need to refill my water. Can I?
I can bring it if you continue.
Thank you. Okay, so that's a t-dester, and I'll always mean that it's slightly generalized. And then if you think about those guys, in fact, it's enough to just think about the Bohota-Davis example. You'll see that you must exclude something that looks like that, otherwise you're not going to get a family that rules out that example. Okay, so that's one graph. So then we worked even harder, and we characterized all the finite families, excluding which causes the T-clean graph to have bounds to it. And so H is final. So I understand what that means, and I'm not going to tell you the answer, but more or less the answer is you figure out what you need to exclude from this. You know, what finite families you need to exclude to disallow this. And then you prove that that works. Okay, so, and then we sort of weren't sure what to do, because we did one graph, we did finite families. We don't have a conjecture for what all obstructions look like. So we need some conjectures that, something general you can say to describe all obstructions. Maybe not an explicit description of them, but some properties that they all have. Throat is still dry from hours and hours on the plate. So, okay. And so Sepher Hajebi came up with a conjecture that did that. It didn't list all obstructions explicitly, but it picked up on some properties that they all had. And the property was that every graph of sufficiently large treewidth has 2 anticomplete subgraphs of large treewidth. So, except I need to qualify it a little bit, because otherwise it's not true. For example, the click doesn't, or the complete vector graph doesn't. Or, a little harder to see, but still true, this graph doesn't. So, but it turns out, if you exclude those, then it's true. So, G doesn't contain a KT, doesn't contain KTT, doesn't contain a t-dester in this generalized sense, and has large treewidth. Then it has 2 subsets anticomplete to each other, each with large treewidth. That was conjectured by Sepher, and we proved it, and I'll spend the rest of my talk.
So they are disjoint, right?
Disjoint and anticomplete, yeah. Anticomplete means no edges between them. And so I'll say something about the proof. And we just proved it in Barbados in March. So it is all a little new and hopefully true. Okay, so proof. And I'll skip it. So first of all, I claim I can immediately restrict my attention to T-clean graphs, because if you have a huge wall, take its top left corner and bottom right corner, and these are 2 slightly smaller walls anticomplete to each other. If I have a line graph of a big wall, do the same thing, and it's 2 line graphs of walls. So really, secretly, it's a problem about T-clean graphs. And I'm not going to be sort of serious about numbers. Every number is steep and teasing. So then the next fact is not a mathematical fact, but a fact of life. We've been thinking about graphs with large treewidths for many years now. And so we know a lot about them, and we're able to pull a lot of lemmas from different places and different proofs. So I'm just going to tell you something about some of the lemmas. So first of all, so remember Davis's example? Over there. So what if you almost contain it? What do I mean by that? So you contain a bunch of paths anticomplete to each other and a bunch of vertices, each with a neighbor on each path. But I didn't tell you anything about how these neighbors behave. Can you say something? So that's a graph of large treewidth because it has a k to t minor. What can you say about it? Can you sort of say it has to contain an induced subgraph this or this or that? And turns out the answer is yes. So we can characterize, if you look like this, we can, let's list which induced subgraphs of large treewidth you have to contain. So the Death Star is one of them, and then there's another one. And I'll tell you what they are, but it's a useful fact to know. It's multi-Death Star and multi-zigzag, but I won't tell you what they are. So then the second lemma is a nice lemma that says if you have a set of vertices always with neighbors in a fixed connected graph, then there's a big subset of them that attaches in this connected graph kind of neatly. And neatly means, so I've drawn some of the words. Practically, I can just stare at this. So the pink vertices, right, so I have started with a set S and a connected graph X. And then you can choose a subset of S, right, so some pink vertices, that attach in this connected subgraph in a very organized way, like this or like this. Okay, so these are two lemmas that are useful to us.
So this lemma too, you don't assume cleanness, or do you?
No, you don't assume cleanness. That's just general. So now there are two cases. The one case is when your graph contains a big, complete graph as an induced minor. Now, if you don't know what an induced minor is, I'm not going to tell you what an induced minor is, but I'm going to tell you what a complete bipartite induced minor is. And what it is, it's M connected subsets here, and M connected subsets here. These are called A1 through AM. These are called B1 through BM. And the rule is those appear as anticomplete to each other. Those appear as anticomplete to each other, but between top and bottom, everyone on top has an edge to everyone on the bottom. So it's like a minor, except where you don't want an edge, it has to be anticomplete. So that's what a K, and you can probably deduce what a general induced minor is, but that's a KMM induced minor. So, okay, so you start with this KMM induced minor, and you start thinking, how can I clean it up? What does it have to look like? What do you know? Try to make it minimal. Where somehow I don't mind making it a little bit smaller, but neater. Right? Smaller but neater is better. So contract the B sides, and now suddenly you have connected subgraphs A1 through AM, and vertices B1 through BM, and each of the B's has a neighbor in each of the A's, and you deal it with this lemma, and you can assume it's all the same by taking a look at 1/5 of the A's, and then it turns out that almost always it's very nice for you. So could it be this case, where the way you attach is by a big click? Well, no, because we forbid K to T. Could it be that it's always that case, where the way you attach is by this kind of subdivided star? Well, then something good happens. Right, so that's what it looks like. You can assume all the A's are just subdivided stars, and the B's just see them at the leaves. And then you take half of the A's, and you just keep the rays of the star that attach to the first half of the B's. And you take the other half of the A's, and you just keep the rays of the stars that attach to the second half of the B's. And that's two anticomplete subgraphs with large treewidths, because this still contains a big complete bipartite minor. what you kept from these plus the left part of the piece, left half of the piece. This has a big biptyte minor. It's what you kept of these versus the second half of the piece, and they're anticomplete to each other. That's how it works. So let's do another case. Maybe it looks like this. Like maybe the connection was like that. So, but it's the same deal. You can take the left half of the pass with the first half of the piece, and the right half of the pass with the second half of the piece. And again, it's two anticomplete graphs, two large treewidth graphs, anticomplete. And then turns out what you always get is you always get this case. So A is a pass, and B's somehow have neighbors on this pass. And then you swap the roles of A and B, and now B's are also a pass. So your induced minor is just a bunch of pass on top and a bunch of pass on the bottom, and edges between them. And that's a hard case that I'm not going to show you how to do. But this level is useful. So now let's skip that. That's lovely. And now we're in the second case, where there's no large induced complete biptyte minor. So now we pull out of our pocket another lemma that we proved in the course of this project. So remember, I told you that if you have this picture, a bunch of paths anticomplete to each other, and a bunch of vertices, each with neighbors in the path, each with neighbors in each path, then we understand what they have to contain. So we cannot prove that that you always must contain that, but we can almost get that. So that's just not the right thing to say. So what we can do is what we call a semi-induced complete biptyte minor. So what's a semi-induced complete biptyte minor? It's a bunch of paths like this, and a bunch of paths like that, and each of these attaches to each of those. And these appear as anticomplete to each other. But here, there could be edges between the paths. So it's like this. It's almost an induced minor, except the B's are not anticomplete to each other, but on the flip side, I can promise that they're all paths. And I'm not going to show you the proof, but it's something you can get. So I don't have an induced complete biptyte minor, but I do have this picture, and somehow it's now all very close. Finish it. So what you do is you take, right, so it's the same picture, there are edges between the P's. So now, oh yeah, and one thing I forgot to say. So it's path versus path, but also everything is in order. These paths, it attaches the first segments of the horizontal paths. And the second path only attaches in this segment. So what I'm going to do, I'm going to break this horizontal path into a few intervals, each containing the attachments of a bunch of those. So like this. The green intervals which contain the attachments of the first 10 paths. The red intervals contain the attachments of paths 11 through 20, and so on and so forth. And now I'm going to define a graph that tells me how colored intervals of these paths interact with colored intervals on that path. Right, so it's a biptyte graph whose vertices are, let's say it's for path I and j, but I can only reach paths s minus 1 and s over here. So the vertices of the biptyte graph are the colored interval in path color intervals in path a minus 1, s minus 1, and the colored intervals in path s. And there's an edge between them. So let's say there's a green to red edge. If this green has an edge to this red. So it's like it's from top to bottom. So for every two paths, it's a biptyte graph, right? That tells me how the intervals interact. And I have lots of paths and relatively few of these intervals. So I can start homogenizing everything. And I can assume between every path it's the same graph. Between every pair of paths it's the same graph. And so now I ask, what does this graph look like? So and it turned out all I'm going to ask is it a complete vector graph or is it not a complete vector graph? So if it's not a complete vector graph, it has a non-edge. So let's say I had a non-edge from green to orange. So I have lots of this paths, and for all of them I have the property that a higher green is anticomplete to a lower orange. Right? That's what it is. So then it looks like this. I take a bunch of high greens, a bunch of low oranges. There are no edges from here to there. These horizontal paths attached neatly to begin with. And that's two large subgraphs, two anticomplete subgraphs with large treewidths. So this graph between pairs of paths is a complete vector graph. And then that means so it's a complete vector graph. So every top interval attaches to every bottom interval. Now just to take paths 1 and 2. And all of these intervals are adjacent to all of those intervals. But that's a complete vector mine. Just very simple. Subpaths of the first path and subpaths of the second path, and that's a complete vector mine. And which we already assumed. And that's how you finish. Thank you very much.
Thank you. Any questions?
So if you want k subsets of vertices with large tree width that are pairwise anti-complete, can you do this?
Make 2 and now apply the theorem to this one. Just
Yeah.
minus 1 here.
I see.
Do you know any bounds on the function of the tree width, the anti-complete things compared to the tree width?
This proof gives you some bounds.
Some bounds.
You're asking about lower bounds?
Just
Lower
like
bounds
the order of magnitudes or anything like this. No, that's great.
Multi-exponential.
Yeah.
So can you use these properties to design like a stable set algorithm?
Yeah, the truth is bounded.
If you don't forbid KT and KTT, and then instead of anti-complete, maybe you want to say either anti-complete or complete or something like that. KT already is a complete thing, so.
The KTT maybe already does what you wanted, and so now forbid KTT. And if you say anti-complete or complete,
so forbidding KTs.
and then the same for KT.
Okay, so, I try to see whether we can remove the conditions and then try.
Yeah, just like we didn't forbid walls, but we immediately did.
And you say the distance as well? Instead of anti-complete, maybe distance is. Any other questions? Can you say a little bit about lemma 2? Very curious.
Try. Yeah, just to remind myself what it says. Oh, lemma 2?
Yeah.
What kind of
Do you-
things do you want to say?
So here you have no assumption about the so graph.
No assumption about anything, it's just a lemma about general graphs. I suspect out of all these projects, this will be the best part about it. So,
and these graphs are induced subgraphs?
yeah. So notice there's some sort of, the cases are not mutually exclusive as I've drawn them. Like for example, this path could be empty, it could be that he just has a neighbor here. And then is it this case or is it that case? Right? Because then, like, if all of these legs are just one edge, then this is also an instance of a path where they all have neighbors. And if all of these are just one edge, that's also an instance of a path where they all have neighbors, just a very short path. So there's some, it's convenient to resolve this lack of disjointness differently in different circumstances.
All right, any other questions? So,
No, I was wondering that this picture really reminded me of this very interesting line of work about characterizing monadically dependent graph.
What's that?
Monadically dependent graph. Okay, right. So anyway, so I can explain about that. But in some like, so it's a graph class where which is not as complicated as the class of all graphs, in the sense that you cannot default transduce the class of all graphs. They want to have a combinatorial characterization of this class, and on the way, they want to extract some like a forbidden. So they have a forbidden subgraph characterization, but like there is some flips involved in that. I think they really like extract something very similar. So
I think we're not
Yeah.
the only people in the world who discovered this thing. I
Right,
think
right.
everybody knows
Yeah,
some
yeah.
version of it.
all right, any other questions? Okay, then let's thank the speaker. Yeah.